So now that we've explained what PL is all about in ordinary words, we can look at the formal syntax of the language. Um, okay, so first of all, in SL, remember, every compound sentence is built out of smaller sentences, and these smaller sentences have definite truth values. So, for example, this compound sentence here, this is built, the immediate components that it's built out of are A and B and D or E. These are things that have definite truth values. And then this one is going to be built out of two sentence letters, A and B. Sentence letters have truth values. This is built out of D or E, or D and E, right? Those two sentence letters, those have truth values. PL doesn't work that way, right? So if you take, for example, for all x, fx, what this is, the way that you build this in PL is by taking fx and then you put a universal quantifier in front of it. Um, But fx here, right, you've got this variable and you have no guide as to how you're supposed to interpret it, right? You have a variable, but with no quantifier there, you don't know how many objects in the universe of discourse the variable is supposed to apply to, right? Whether it's supposed to apply to everything in the universe of discourse or one thing in the universe of discourse, et cetera, et cetera. So this doesn't have a truth value, right? Whenever you're building sentences in SL, you're always building compound sentences out of things that have truth values. You're not doing that in PL. And so what PL does is PL distinguishes between formulas and sentences. Formulas are what sentences are ultimately built out of, but formulas don't necessarily have truth values. Sentences do. Um, Formulas, I should say, formulas are going to be defined recursively. And then sentences are basically defined as those formulas that all will have truth values. So first of all, we define the atomic formulas. Atomic formulas are going to be the base case in our recursive definition. An atomic formula is a sentence letter. Remember the PL contains sentence letters. Um, It's a sentence letter or it's an n-place predicate that's followed by n individual terms. And the individual terms here can be constants or they can be variables. So either of those can be found in an atomic formula. Um, and just as a note here, atomic formulas never go in parentheses, right? So none of these are properly written atomic formulas. So having defined that, we can give the recursive definition of a formula of PL. So remember that a recursive definition of a set there's a base case of things that fit the definition, and then you have an inductive step that tells you how to take things that fit the definition and turn them into more things that fit the definition. And then you'll have a proviso that says that nothing is a member of the set except for the things that have been specified as fitting that definition. And so all the different parts of this have been labeled here. So here's your base case. Any atomic formula is a formula of PL. And then you've got a three-part inductive step. So these two parts here, these are basically this is basically just the inductive step from the definition of sentences of SL, right? If you have a formula of PL, then its negation is a formula. If you've got two formulas of PL, then the results of adding the sentential connectives of SL make more formulas. This is the new one here. If you have a formula of PL and it has at least one occurrence of a variable x, and there isn't already an x quantifier, then the result of putting a universal quantifier with the variable x or an existential quantifier with the variable x are formulas. And then, of course, we have the proviso, right? Nothing is a formula unless you can form it by repeated applications of 1 to 4. This step 4 here, what this does is it rules out uninterpretable strings like what we were looking at in the last video. So you can't have overlapping quantifiers with the same variable, right? In these here, these get ruled out because at the previous step, you already have an X quantifier, so you can't put another one on. You also can't have mismatched variables. So in these ones here, you can't have, I mean, in this case, right, um, this violates the requirement here that you have to have at least one occurrence of the variable and the quantifier in the sentence in both of these. So these don't count as formulas. Okay. Our informal conventions are the same as in SL, right? We drop the outermost parentheses and you can replace parentheses with square brackets. Note that you can't drop the parentheses around quantifiers. You can't change the parentheses around quantifiers to square brackets. And you can't drop the parentheses around the immediate subformula of the quantifier, right? So here, for example, this is the immediate subformula of the quantifier. You can't drop the parentheses around that. Then it becomes unclear how much of this that quantifier covers. Oh, and when you put when you put a quantifier on an atomic formula like this, don't add parentheses to it. They still don't get parentheses when you put a quantifier on. Okay, so logical operators. The logical operators are the sentential connectives of SL plus the quantifiers. The main logical operator of a sentence is the main connective, same way as it's defined in SL, or the quantifier that is furthest to the outside. Um, Most of the time you can tell what it is, right? If you're, you'll be able to tell. I mean, the main connective is going to be identified the same way as it is in SL. A lot of the time, the outermost quantifier is pretty obvious. It's the one on the outside. Um, where it gets a little trickier is where you have sentences that have both quantifiers and sentential connectives, because then people will get confused as to which one, whether it's the connective or the quantifier that is the main logical operator. So things like this, for example. Um, in this one here, right, because of the parentheses, that means that this quantifier covers this entire part of the sentence, right? This entire formula here is covered by it. So because of the fact that that covers the whole thing, this is your main logical operator. Here, the quantifier only covers this little bit here, the LX, right? This is actually outside of the scope of that quantifier. It's not covered by it, which means that this is the main logical operator. Right. So this sentence, this is a quantified sentence, universally quantified sentence. This is a conditional, where the antecedent is something that's universally quantified. So, subformulas, this is the PL version of subcomponents from SL. Um, I don't think we need to go through the entire definition in a ton of detail. You can read about it in the book. Okay, scope. So the scope of a quantifier is the quantifier plus the subformula that immediately follows it. So in particular, right, the scope of the quantifier is the entire formula for which that quantifier is the main logical operator. Um, and then a variable is bound if it occurs in the scope of a quantifier that uses that same variable. Otherwise, it is free. So if you look at these three sentences here, right, or formulas, sorry, these are not sentences. Um, in this formula here, um, both of these variables are free, right? There are no quantifiers that apply to these. So they're not in the scope of any quantifiers at all, right? So they're both free variables. In this one here, the x is bound because it is within the scope. The scope of this quantifier is this formula here. The x here is within the scope of an x quantifier, so it is bound. The y is free because there is no y quantifier. And in this one here, both of the variables are bound. The x is within the scope of this quantifier. The y is in the scope of this quantifier. Note that if you look at this last sentence, you can see the differences between quantifier scopes. So the scope of this quantifier is this. The scope of this quantifier is this. This one is the entire sentence. This one is just this right here. Okay. Having defined scope and then the difference between free and bound variables, we can now define a sentence of PL. A sentence of PL is just a formula that doesn't have any free variables in it. So this is going to be, and actually you can specifically say, so an atomic form or an atomic sentence is an atomic formula that contains constants, but no variables, no free variables. And then any other sentence is going to be one that is either a truth functional compound of atomic sentences or contains quantified sentences where every variable is within the scope of an appropriate quantifier. Formulas that are not sentences are sometimes called open sentences. This is a bit of an older usage, but it's still something that's fairly common. So that's the definition of a sentence of SL, or sorry, of PL. And the reason for this, remember, is that these here, formulas with no free variables, these are the entities of PL that always have truth values. The so-called open sentences, the formulas that are not sentences, these don't have truth values because they have variables in them that can't be interpreted. Now, there's one last definition that we need to give before we're done with formal syntax. That's the notion of a substitution instance. So a substitution instance of a quantified sentence is what you get if you take off the outermost quantifier, and you can only take out the outermost quantifier. You can only go, substitution instances only work from the outside in. And then you replace every variable that's bound by that quantifier with the same constant. So these are all substitution instances of this sentence here. Right? You can take that y there, you can replace it with any constant. Note that you couldn't go and replace that x with anything because that's not the outermost quantifier. The way that you write a substitution instance is like this, and the constant is referred to as the instantiating constant. This is something that gets very important when we start doing derivations for predicate logic, because we need the notion of a substitution instance to define the rules that we're going to use in the derivation system.